adjusting this new height. I've put the phone on top of something to give it a little bit of a height. I don't know if this is better or worse. I was hoping for better. But here I am. I am live. We're live. Welcome to the live. Welcome. Thank you so much for being here. Join us. Welcome. Actually, let me move this a little bit. I don't know. What do you think? What do you think of this new angle? Nathan, Steven, Doro, Reese, how is everybody? What do you think of this new angle? It's a little elevated. Do you see any differences? Is this any better? My face is still a face. Hello, Wonder Boy. Hello, Nathan. Hello, everybody. Welcome one. Welcome all. Welcome to yet another episode of Black Holes by Stephen Hawking from his book, A Brief History of Time. We will catch up first and hang out first and say hi to everybody first and read all the comments and read your usernames and do any shout outs that come in first. And then we will launch into this most exciting topic of black holes yet again for another night in a row. We will talk about continue to talk about black holes from this book, Brief History of Time by Stephen Hawking, sorry. Not Hawkins, like the pressure cooker, but Hawking with a G. Make sure to like. Thank you so much. Please do like the live. Can we get 20 likes? So I see, hello, Wonder Boy. Hello, Nathan. Hello, Steven. Hello, Nathan again. Nathan says no difference. Oh my gosh. Well, Nathan, I brought out a very, very big book, which I'm using to elevate the camera a little bit. But you're seeing no difference, which is fine. Wonder Boy says, hello, Steven. Steven says, make sure to like. Thank you, Steven. Did you like? I see no likes so far, so please do like the live. Thank you so much for being here. Thank you so much for liking the live. Can we get 20 likes? And we will get started and I will share the live. Today is quite cold here in Boston in North America. It is a little chilly. It has been raining all day. And hello, ASMR. Can you please give me a shout? My name is Olivia. Welcome, Olivia. Yes, of course. Here's your shout out. Everybody say hi to Olivia. Say hi to ASMR. I love it. Steven Spears says, I did like, I'm the only like so far. Oh my gosh. Steven, you're the best and thank you so much. Nathan and Wonder Boy and ASMR, could you please like the live? And could you hurry up and like the live? That would be wonderful. Wonderful. Hi, Nathan. Hi, Olivia, says Steven. See, Steven is a nice guy. He says hi to everybody. He sneaks into class without being seen. And he asks the most delightful questions. So, thank you, everybody. Thank you, Steven. Thank you so much. Thank you. Welcome and like the live. KJ Kylie says, how are the Bruins doing this year? You know, if that is a sports team, I am not super familiar because I'm not super into sports. But thank you for being here and thank you for the question. ASMR says, I like the live. Thank you, ASMR. Thank you, everybody. Welcome. If you would like to put something in the chat, go right ahead. I will give you a shout out. I will look at your name and I will read it out and read out your chat message. KJ, thank you for being here. Welcome. This is a Kitty Cat plus physics channel. We talk about cats and educational content, including physics, astronomy, cosmology, astrophysics, and of course we chit chat, we hang out. There are people who are friends with other people in the chat, in the live, that they met right here on the live, and there is a delightful time to be had usually during these nightly lives. The Warrior says, when are you going to tell them you were born a man? The Warrior, a very nice username, and Reese, that's okay. They can think I'm a man. I am, basically. Combat Sports, hello, Combat Sports. Hello to USA, hello to France, hello to Britain, hello to North America, South America, Asia, Europe, Africa, Australia, New Zealand, Antarctica. I was reading a comment, and so I got stuck a little bit. Rose Dawson and the Titanic, and do not forget I'm an iceberg. Steven is an iceberg. He is an iceberg on the chat. Reese says, bollocks to them. I don't know what that means. Actually, what is the meaning of this bollocks, Reese? Do elaborate. Kylie, hello Kylie, heart. You're so pretty, says Kylie. Thank you so much. Thank you, darling. How are you? Thank you, everybody. Thank you, one. Thank you all. Welcome to the live, and thank you for being here. Faze, F-A-S-E, Faze says, I can tell that you have a brilliant mind. Oh, well, thank you. Thank you, thank you, thank you, thank you, thank you. Apparently, I'm a man. Does that mean I will make more money? I'm all for it. I mean, I could elaborate, but I'd better not. Means stuff them. Stuff them. Oh, stuff them where? Stuff them where? Goodness, I don't have any spots for stuffing anybody anywhere. All the spots are taken. I don't actually, I don't even know what that means. Combat Sports says, what is the topic today? It is black holes. We're still on this book, A Brief History of Time by Stephen Hawking, where we've been covering the topic black holes, which is what he has largely contributed to. Stephen Hawking, that is. And, Stephen Hawking almost didn't do his PhD because he thought he was going to die. But then his condition, I guess, was more stable than expected. And he wanted to get married. And for that, he needed a job. And for the job, he needed to have a PhD. And so he did get his PhD. And he contributed very nice things to the topic of black holes, which we will learn more about today, right here, right now, with you, with us, with all of us and the kitty cats. Let's see if Baji's behind me. Not yet, not yet. But thank you so much for being here. Thank you. Welcome all. Welcome one, welcome all. And please do like the live. Could we get 10 likes? Could we get 20 likes? I only see 2, and it is quite a depressing amount. Wonderboy says, not literally stuff them, forget it, lol. Wonderboy and I were on another live just a bit ago. Really? Which live, Nathan and Wonderboy? Which live? He died of Lou Gehrig's disease. Sky, I think I saw you. Goodness, are you guys going to other lives too? I feel rather sad about this. I don't know if this is allowed. I thought you guys came to only my live. Goodness. Will you talk about LIGO and Virgo? Nathan, you were waiting for me. Oh my goodness. Oh, thank you. That makes me feel way better. Better indeed. So LIGO and Virgo, we can certainly talk about LIGO and Virgo. These are, of course, the gravitational wave observatories, especially the Laser Interferometry Gravitational Observatory, which is what LIGO stands for, is the first experimental measurement of, or the first measurement and the first experiment to have measured gravitational waves directly coming from some cataclysmic events in the sky involving certain neutron star, or neutron star black hole merger. I forget exactly what the merger involved. It could have been a neutron star pair or a neutron star black hole pair, which was the first measurement. They have a couple. And it was indeed a very big deal when this news came out. I was in graduate school myself. And it was the first direct measurement of gravitational waves, making it an extremely historically important, significant event and confirmation, of course, of Einstein's general theory of relativity, which predicts the whole gravitational wave thing. Although we had measured gravitational waves indirectly by looking at basically the gap between two binary pairs kind of becoming smaller and smaller as two compact objects revolving around each other releases gravitational waves, and or another way of saying it, gravitational energy, which makes the gap between them smaller and smaller, and ultimately leads to them colliding, and that would lead to another sort of big explosion, cataclysmic type of event. So we had an indirect measurement of gravitational waves or gravitational energy, if you will, before this direct measurement by LIGO. So that is where LIGO is extremely important, extremely significant. So thank you for asking about LIGO. Today, we will look at Stephen Hawking's work on black holes and his insights on black holes. So we might not get into LIGO too much, but he does actually, even Stephen Hawking has actually mentioned LIGO. It was before, or sorry, it was after his time. If Stephen Hawking was still around, he would have given more comments on LIGO, I'm sure, LIGO and Virgo, I'm sure, because these experiments are extremely important with these types of measurements of gravitational waves. And so I think a lot of people predicted these things and were not around to see the prediction come true. For example, Einstein predicted gravitational waves a long time ago, and he is, of course, not around to see the experiments and the measurements of these instruments. So it's almost like something very important predicted 100 years ago is being measured directly now, because we've vastly improved in our experiments and measurement abilities and observational abilities and our technology for observations. So that's what LIGO and Virgo is largely. It is something coming true, something being measured in real life that would have been predicted a long time ago, about 100 years ago, if not more. And actually, it might have been exactly 100 years ago-ish, because I think it was around 1917, and the 1920s were, of course, very important for relativity, quantum mechanics, and all that. And then it was around 2015, 2016, 2017 when LIGO was coming out with its first results. And of course, we also have talked about a little bit about LISA, which is a LIGO type of experiment that we might put on a spaceship and have it sort of be in orbit around the Earth, and being able to measure gravitational waves directly from space, because of course, as you know, on Earth, making these instruments is quite difficult. Earth has a bunch of other types of things that would kind of lead to the noise of the experiment, vibrations and things like that. These experiments have to be extremely accurate, extremely precise. And on Earth, the types of events that we would be sensitive to would have to be the even larger, even more explosive and bigger explosion and bigger cataclysmic type of events. Whereas in space, where we don't have to worry about Earth vibrations, we might be able to be sensitive to sort of events with the lesser gravitational energy. So so that's what is kind of in the future, actually, for us. I'm still on the topic of gravitational waves. It's a very good topic that Combat Sports brought up. But that's kind of in the future. We don't have this space gravitational observatory yet. But if we have that, then we will see stuff from there as well. So thank you for that question. Combat Sports asked about LIGO Virgo. Very nice. Basically, gravitational wave observatories, measuring gravitational waves directly for the first time. Very big accomplishment in science. Nathan says, waiting for you. Sorry. Thank you for waiting. Steven says, ALS, we're always waiting for you before and during your streams. Water break time. Thank you. Thank you. Thank you, everybody, again for being here. Please do like the live. Can we get 20 likes? Nathan Mullins says, thank you for the emoji. Nathan, impressive. You know everything about physics. Combat Sports says, well, I don't know everything. I actually don't know too much about condensed matter physics. So I should know about particle astrophysics, cosmology, astrophysics, astronomy, because that's sort of my area. But I don't know too much. In fact, I know quite little about condensed matter physics. See, the thing about being sort of an expert in something is that you know something, and then you also hopefully know what you don't know. And what I don't know is condensed matter physics. but I hope that I know something about astronomy, astrophysics, particle physics, because that is where I worked. Got my 14 review on my little business page today. 14th review. Oh my goodness, congratulations. Tomorrow I'm going to start building a workshop in the back garden. I grew up with Carl Sagan and his TV show Cosmos. Good job, Steven. I did my own lawn care for about 4 years. Look at all the business owners in the chat. Congratulations on your businesses. I love seeing stuff coming from the James Webb. Yes, yes. Our space telescopes are really, of course, including my favorite one is Hubble. Hubble really has given us everything. I mean, the person Hubble and also the Hubble Space Telescope has given us so many amazing observations that has really opened up, quite literally, our eyes to the rest of the universe. Nice. We need electronics these days. I know nothing of these fields. Sorry, B. Oh, no worries. That's, you are here. You will know a lot more, I hope. Especially after they fix the optics. Okay, so everybody, thank you for gathering. Thank you indeed for being here. Really love it that you are here. And this party is getting started. Doro is here with his original username. Hello, everyone. Party time. Yes, I will learn. The transport boy. Oh my gosh. Hello, transport boy. I'm in London. Goodness. Hello to London. Welcome, London. Welcome, Belgium. Welcome, USA. Welcome, everybody. Doro is in the house, indeed, near the Shard. Near the Shard. Okay. 20 likes are needed. Let me pin that message. Thank you for liking. Thank you for subscribing. Thank you for sharing. In fact, I should share the live. I forgot to do that. Party man is in the room. Indeed, indeed, we are here. We have gathered. Let me share the live on my channel from this broken phone because I always forget to do that. The Shard, it set fire to stuff when they first put it up. I'm not familiar. 5K subs for this stream goal. Oh my gosh. Thank you, Transport Boy. Thank you so much. Please do share the live with the entirety of London. That would be amazing. Faze says, this feels like a college class. It is like a college class, Faze. Thank you for the observation. Thank you so much. But see, college sometimes costs $60,000 per year. This is free. So I hope you appreciate that, and I hope that you will stay for the entire live and listen to what we have to discuss here today. And welcome one, welcome all. Thank you, and please do like the live. Can we get 20 likes? She will have 5K subs soon. Thank you. I hope so. Thank you, universe. I'm his evil opposite from the mirror universe. Beware. This is like a college class, but also with a wild party scene. Exactly. There is a party that's about to begin in the chat. Please do join it if you want to, or listen if you want to, and or do both if you want to. Transport Boy, thank you for the emojis. Thank you, everybody, indeed. What a delight to see you all. Let me turn off the volume of this phone and click on my live and share it with my channel. Do both. Learn while things go insane. Indeed, things are about to hit an insanity levels unparalleled in any other chat. So welcome one, welcome all. Transport Boy says that is good angle. Indeed, indeed, these people that join this live are one of a kind indeed. For example, Stephen sank the Titanic as he is an iceberg. Not being mean, but I was behind a Jeep earlier that had a crazy cat lady sticker, and I thought of you. You should think of me. In fact, you should think of me so much you constantly share my channel with every car that you encounter. You should roll down your window and tell them, follow Baji the Handsome Cat on YouTube. It's completely free and comes with educational content. Passes out wine glasses and sets out bottles of non-alcoholic. Did you know that at my PhD defense, we had non-alcoholic sparkling wine? That's mean. The tube is so busy today. I'll take over an entire building to promote your channel. Oh my gosh! You should. You should. You should feel free. Feel free. Feel free indeed to buy a building and put my channel's advertising on top of it for free because we're friends. We're friends. We're online live chat friends. Feel free to buy a building and put an ability to share my channel on the building. Welcome one, welcome all. We are live. Join us, chat with us, hang out with us and listen to this live. Okay, we will begin. Not gonna buy it. We are definitely internet pals. I'll commit felonies for your channel. Aww. Oh, you're gonna acquire it in a different way. I see. Your cat is so cute. Thank you. I don't know which one you mean, but they're all very cute indeed with the grace of God. Thank you, universe, for your help, support, protection, blessings, kindness, and guidance, especially for the cats. And me for taking care of them so I can take care of them. Okay, we will begin. During the gravitational collapse of a star to form a black hole. Thank you. The movements would be much more rapid, so the rate at which energy is carried away would be much higher. So this is the thing that I was talking about a minute ago, based on somebody's question there about gravitational wave experiments, which is that when some sort of cataclysmic event, explosion, some star dying, some other star dying, some compact objects that are in a binary colliding, etc., or even if they just do a little dance of revolving around each other, you're actually constantly losing gravitational energy. Okay, and how rapidly you lose gravitational energy from a certain system depends on how big, how dramatic this event is, how cataclysmic, what kind of explosion, etc., okay? So it would therefore not be too long before it settled down to a stationary state. If it lost a shoot ton of gravitational energy, then it could settle down to a stationary state. On the Real Channel, hello Doro, hello Transport Boy, hello everybody. Did you hear about the black hole that's bigger than the Milky Way? Hello John Foster. Great kitty content lately. Seeing a lot of Baji and Suji. Thank you, Varun. Oh my gosh. Love it. Thank you so much. Baji is not behind me yet, but thank you so much for enjoying the content and liking and sharing and subscribing. Most kind of you, and thank you and welcome to the live. And please do like the live, and can we get 20 likes? So what would this final stage look like after a system has lost gravitational energy? One might suppose that it would depend on all the complex features of the star from which it had formed, not only its mass and rate of rotation, but also the different densities of various parts of the star and the complicated movements of the gases within the star. And if black holes were as varied as the objects that collapsed to form them, it might be very difficult to make any predictions about black holes in general. Oh, really? Oh, goodness. Oh, wow. That's amazing. I don't think I've heard too much about this black hole, but thank you for telling me. Imam, hello. Salam alaikum. How are you doing? It came across my news feed that a high schooler discovered it by accident. I watch Audrey and Noah the cat streams almost every day. Thank you, Steven. Oh my gosh, how very nice of you. It wouldn't let me say commit crimes. Oh, hello, El Challen. Oh, thank you, everybody. Most kind of you. That is so nice. In 1967, so if we had to depend a lot on a lot of different variables of a star in order to understand what kind of black hole it would form after it has collapsed into one, then that could be a lot. Stars are very, there's a lot of variety of stars. There's a lot going on in a star, but we will see what Stephen Hawking has to say about that. As far as when it does collapse into a black hole, what are the things that are sort of important to know? In 1967, however, the study of black holes was revolutionized by Werner Israel, a Canadian scientist. So his name is Israel, but apparently he's a Canadian scientist who was born in Berlin, brought up in South Africa, and took his doctoral degree in Ireland. What a global personality. So his name is Israel. He was born in Berlin, brought up in South Africa. How amazing. And took his doctoral degree in Ireland. Israel showed that according to general relativity, non-rotating black holes must be very simple. They were perfectly spherical. Their size depended only on their mass, and any two such black holes with the same mass were identical. So even though stars may have a lot of complexity, complication, etc., black holes that come from those stars, like once the star has collapsed and done its thing to become a black hole, basically it has died, to then give you a stellar remnant, which is in this case a black hole, again depending on the initial mass of the star, then that black hole is actually more simple than one might think. It pretty much kind of just depends on the mass, and if it's especially a non-rotating black hole, then it's very simple. It's very simple, perfectly spherical, and the size depends only on the mass. And any two such black holes, doesn't matter which stars they come from, any two such black holes with the same mass were basically identical. They could, in fact, according to this, they could in fact be described by a particular solution of Einstein's equations that had been known since 1917. So this is the year 1917 that I was recalling when we were talking about LIGO as well. I believe, so 1917 was an important year for general theory of relativity, and then 100 years later, around 2017 is when LIGO came out with its measurements. So it's really quite cool. Einstein was, of course, very ahead of his time in that sense, that he made theoretical predictions with his theories about gravitation that weren't quite experimentally directly observed and measured until 100 years later. So wish he was here for that, but you know how death works, how people sometimes die. So anyways, they could in fact be described by a particular solution of Einstein's equations that had been known since 1917, found by Karl Schwarzschild. So now, thank goodness, we will talk about Schwarzschild, who is extremely important for black holes. So if you remember from Einstein's Cosmos, the book written by Michio Kaku that we also discussed here, if you remember, Einstein's general theory of relativity equations were not always exactly solved. But one of the first cases where it was exactly solved was for a black hole by Schwarzschild, if I remember correctly. And this spelling, Schwarzschild, is SCHWARZSCHILD. So the last part is like child, Schwarzschild, but the word is same spelling as child. So anyway, in 1917, found by exact solution of Einstein's equations in 1917 by Karl Schwarzschild, shortly after the discovery of general relativity. So when Einstein is working on general relativity and coming out with it, soon after, Karl Schwarzschild worked on finding an exact solution of these equations in the form of equations for a black hole. And remember, at that time, people didn't quite believe in black holes. They thought that, okay, this might be an exact solution of these equations, but surely these things can't be true, can't be real. And they sometimes call them dark star, point star, or black hole. But sure enough, these things are actually quite real, and we have seen them in nature. Hello. Thank you for joining the live. I'm trying to read that. मैंने इंदिरा गांधी को देखा, लेकिन ये छोटा था. Are you saying that you've met Indira Gandhi, but you were little at the time? I hope that I read that mostly correctly in Hindi. Thank you so much for that message in Hindi. Acacio, hello. That's a wonderful question. We will absolutely talk about that, Acacio. Thank you so much. In this life, probably. Hola, amiga. Hello, hola. Hola, Acacio. If you had the opportunity, would you go to the space station? The International Space Station? Probably. I would miss the kitty cats, though. I think they send you for months, and that would be a little hard for my Fuji Suji Baji. Ace Wolf Peach says, hey, just a question about frequency reduction of the propeller on a plane. Good. Fake station. What do you mean fake station? Do you not believe in the International Space Station? Wonder Boy. Rose will not share the raft for the others. Not if I can help it. I'm in the house to deal with her. I'm not sure what that comment is about, Stephen. I think I'm reading something in the middle. But yeah, I'll let you guys keep catching up with each other while I do this. And I'll come back to your question about time and singularity. We actually kind of briefly talked about time and singularity from this book. I mean, in fact, this book, it's very relevant. Your question is very relevant to the contents of this book. So they could, in fact, be described by a particular solution of Einstein's equations that had been known since 1917, found by Karl Schwarzschild shortly after the discovery of general relativity. At first, many people, including Israel himself, argued that since black holes had to be perfectly spherical, a black hole could only form from the collapse of a perfectly spherical object. Any real star, which would never be perfectly spherical, could therefore only collapse to form a naked singularity. So there's a singularity there for you. I believe it was, who asked the question? It was maybe Acacio who asked this. So we talked about how time, the concept of time, just to answer the question really quickly, because I'm at the end of a certain paragraph here, but I'll continue the black holes in just a bit. Basically, the concept of time in physics is whenever the universe got started. So according to many in the physics field, the universe got started with the Big Bang, which is an event which is in itself a singularity. And the concept of time basically gets started then. Now, you may believe in a concept of time that is earlier than the Big Bang for some other reason, like religious reasons or spiritual reasons. But in physics, the concept of time really comes from the beginning of the universe with the Big Bang. Now, in terms of singularities, there are two types of singularities that we are aware of that are not fully, let's say, they're not fully described by general theory of relativity. There's sort of a, how shall I put it? There's sort of a limitation. But anyways, these two singularities, one of them is the Big Bang. The Big Bang itself is a singularity. And the beginning of time, the event that caused the universe to start, basically, is itself a singularity. And then another singularity is actually black holes, the one we're discussing right now. So hopefully you will get a lot of insights into black holes from this. And a black hole is a different type of singularity than the Big Bang, but in itself, it's also a singularity. And we will see kind of a description of it here. So hopefully that helps. So keep going here. There was, however, a different interpretation of Israel's result, which was advocated by Roger Penrose and John Wheeler in particular. They argued that the rapid movements involved in a star's collapse would mean that the gravitational waves it gave off would make it ever more spherical, and by the time it had settled down to a stationary state, it would be precisely spherical. According to this view, any non-rotating star, however complicated its shape and internal structure, would end up after gravitational collapse as a perfectly spherical black hole whose size would depend only on its mass. Further calculations supported this view, and it soon came to be adopted generally. Also, I wanted to say that if you're interested in the time discussion and the singularity discussion, it is available in the live stream called, I believe, Expanding Universe, a few live streams ago. But I'm also happy to talk about it more at the end of today. So hang tight, we will get there. Okay, Israel's result dealt with the case of black holes. Oh my goodness. Israel's result dealt with the case of black holes formed from non-rotating bodies only. In 1963, so basically he's kind of focused on non-rotating ones. You could have rotating ones, you could have non-rotating ones. Just to be simple, maybe you start with the non-rotating ones, right? So that's what we're talking about here with the person called Israel. But interesting questions today. Somebody asked if I want to work on the International Space Station. I think I would. I would definitely heavily consider it. Okay, Israel's result dealt with the case of black holes formed from non-rotating bodies only. In 1963, Roy Kerr, a New Zealand, welcome New Zealand if you're here, found a set of solutions of the equations of general relativity that described rotating black holes. These Kerr black holes, so this is Kerr, K-E-R-R, black holes rotate at a constant rate, their size and shape depending only on their mass and rate of rotation. If the rotation is zero, the black hole is perfectly round and the solution is identical to the Schwarzschild solution. So Schwarzschild probably did this for a simple case first, and so that makes sense. If the rotation is non-zero, the black hole bulges outward near its equator, just as the Earth or the Sun bulge due to their rotation, and the faster it rotates, the more it bulges. So to extend Israel's result to include rotating bodies, it was conjectured that any rotating body that collapsed to form a black hole would eventually settle down to a stationary state described by the Kerr solution. So there we go. Non-rotating versus rotating black holes. Why is space always dark when the sun is shining? So, if you're near a star and it's up above the horizon and it's rising or already risen, then you see the light from that. And because we are near we're near a star, a bright star, the sun, we get light from there. If you're asking why is space dark, oh, I see. Space is not all dark. It's mostly dark because most of space doesn't have, I guess, most of space has interstellar medium and gases and things like that. It's not thickly populated with stars. If there was a source of light, then you would see that light. And many of these sources of light are very far away. Why not show it in the pictures? Oh, you want to see more pictures here, you mean? Deep impact, I have not seen it. It lights up the world. The sun, yes. When the sun is up, it does light up the world. That is our Earth. Excellent observation. In 1970, a colleague and fellow research student of mine at Cambridge, Brandon Carter, took the first step toward proving this conjecture, which is the Kerr solution. He showed that provided a stationary rotating black hole had an axis of symmetry, like a spinning top, its size and shape would depend only on its mass and rate of rotation. Then in 1971, I proved that any stationary rotating black hole would indeed have such an axis of symmetry. Finally, in 1973, David Robinson at King's College London used Carter's and my results to show that the conjecture had been correct. Such a black hole had indeed to be the Kerr solution. So after gravitational collapse, a black hole must settle down into a state in which it could be rotating but not pulsating. Moreover, its size and shape would depend only on its mass and rate of rotation, and not on the nature of the body that had collapsed to form it. This result became known by the maxim, a black hole has no hair. The no-hair theorem is of great practical importance because it so greatly restricts the possible types of black holes. So it's kind of Thank you so much for being in the Thank you so much for being in the live. Can you please like the live? Please like, please subscribe, please share. Can we get 20 likes? Have you ever seen a picture of space with sunlight? So if you go to a different planet or a different spot in space, it really would depend on whenever sunrise is for you, is when you would see sunlight. Which can be different if you're not on Earth. And whenever the sun goes down, you will not see sunlight anymore. So it really depends on sunrise at the new spot where you're going. Hopefully close enough to the sun to where you can get the sunlight. Or you could go, for example, close enough to Proxima Centauri, some other star, and then as soon as that star rises for you, you will see that starlight again. So the no-hair theorem is of great practical importance. Ah. One second. There you go. Steven's got it. Steven, thank you. So, one can therefore make detailed models of objects that might contain black holes and compare the predictions of the models with observations. It also means that a very large amount of information about the body that has collapsed must be lost when a black hole is formed, because afterward, all we can possibly measure about the body is its mass and rate of rotation. The significance of this will be seen in the next chapter. Black holes are one of only a fairly small number of cases in the history of science in which a theory was developed in great detail as a mathematical model before there was any evidence from observations that it was correct. People did not believe fully about the existence of black holes in real life, in nature, but turns out that all this work to get the math on the black holes paid off, in the sense that they do actually exist, very much so in nature. Indeed, this used to be the main argument of opponents of black holes. How could one believe in objects for which the only evidence was calculations based on the dubious theory of general relativity? I'm sorry. In 1963, however, Martin Schmidt, an astronomer at the Palomar Observatory in California, measured the redshift of a faint star-like object in the direction of the source of radio waves called 3C273. Now, if you remember, we have spoken about 3C273. Who can tell me, quiz question, what is 3C273? Stephen, you're up. Do you remember what 3C273 is? That is source number 273 in the third Cambridge catalog of radio sources. Which radio source did we talk about in the name of 3C273? Maybe on this live, well, on a past live stream. He found it was too large to be caused by a gravitational field. If it had been a gravitational redshift, the object would have to be so massive and so... Yes! Oh my gosh! Look at you! Look at you! Okay, any other guesses? That's an excellent guess indeed, Wonder Boy. Excellent, amazing. If it had been a gravitational redshift, the object would have to be so massive and so near to us that it would disturb the orbits of planets in the solar system. This is an excellent insight by Stephen Hawking. We have talked about this object and sort of the challenges of it once we observed it and sort of what it implied, and it opened up a whole new world. In fact, world is probably an understatement because it opened up a new type of object in this universe. So, yes. So, if it had been a gravitational redshift, the object would have to be so massive and so near to us that it would disturb the orbits of planets in the solar system. So, something when we observe something like 3C273, it can't be that close to us, because otherwise we would have felt it in some other way. It would have been disruptive to our solar system. So when that does not happen, you have to think harder about what this thing could be. And that was sort of the mystery at that point, and we will see the insight on it now. You always see the darkness of space, but you have sunlight. Show us. Okay. This suggested that the redshift was instead caused by the expansion of the universe, which in turn meant that the object was a very long distance away. So, if the redshift is caused by the expansion of the universe, in other words, dark energy, this whole other topic that we talk about very much, which is very intrinsic to cosmology, then it means that this is a very long distance away. Because remember, the effects of dark energy, the effects of the expansion of the universe is not felt nearby. It's felt on a large scale at long distances away. The scope of my science comes from Bill Nye. Bill Nye is a great guy. So, to be visible at such a great distance. So now we've got something which is a radio source. It would be very big if this was a gravitational redshift. So it's not. It's the redshift because of the expansion of the universe, which means that it's very far away and it is visible at such a great distance. The object must be very, very bright indeed, because the farther away you are, in order to still see such a brightness, such a luminosity would mean that it's very, very, very bright. So, the only, once again, to be visible at such a great distance, the object must be very bright. Must, in other words, be emitting a huge amount of energy. So what could it be? What could it be? The thing that it's a radio source, emits a huge amount of energy, is a very far distance away. What could it be? The only mechanism that people could think of that would produce such large quantities of energy seemed to be the gravitational collapse, not just of a star, but of a whole central region of a galaxy. A number of other similar quasi-stellar objects or quasars have been discovered, all with large redshifts. So it was also point-like. That was the other thing. Remember, that's why it's called quasi-stellar or quasar for short. It's basically a galaxy with a very active center, but it's quasi-stellar when we observe it, and therefore we call it a quasar. So correct guess by somebody there. I think it was Reese. A number of other similar quasi-stellar objects or quasars have been discovered, all with large redshifts, but they're all too far away and therefore too difficult to observe to provide conclusive evidence of black holes. So the other thing is that these active galactic nuclei, which is what the quasar is an example of, an active galactic nucleus or an active galaxy with a very active galactic center, which produces most of the luminosity in that galaxy. It's a special type of galaxy where the center, the galactic center of this galaxy is so active, we call it AGN, active galactic nucleus, and it rivals the luminosity of the entire galaxy, as in the luminosity coming from all the other objects in that galaxy is almost outshined by the galactic center of said galaxy. So these AGNs, active galactic nuclei, are types of galaxies. Active galaxies are not very close to us. Thank God, right? We are in a galaxy which is not an AGN, and we're quite far from these sort of interesting or explosive or I don't even cataclysmic active galaxies. We're not in that part of the universe, which is probably nice because instead we are alive and we're here. If it shines on Earth, its rays show us. Why can you only see sunlight from Earth? Why can you only see sunlight? You can, so if you go to the moon, you can see in space, let's say our galaxy or some other galaxy. It really depends on the source of light that is rising and setting. Based on that, you would see sunlight or starlight, depending on which world you're in, ours or another one in our solar system or a different one around a different star. Between the sun and Earth should be light. Yes, that is correct. We do get sunlight when the sun rises above the horizon, depending on just me and old people, just over here talking with my soon-to-be predecessor about old person things. I can be Reese, Did you not like the live? Is that what you're saying? Oh, no pictures of light in space. So when light, so this is an optical question. I see. In optics, light travels in straight lines, roughly. If we get into the detail of light is a wave, light has a particle nature, but light travels in straight lines. And if the sun is not in the field of view of whatever's taking the picture, then it's not gonna see the sunlight. Does that make sense? Even for a satellite, the sun will rise and set. And often the deep space pictures are pictures taken by satellites. Is that what you're asking about? So even for anybody, not just Earth, not just Mars, not just Venus, we should have a picture by now. We should have a, like, you mean I should draw a picture for you? Or from a satellite, we should have a picture by now of sunlight. Thank you. Thank you for liking the live. Yes, Mars, of course. Yeah. Yeah, Mars has seasons. Mars, as far as I know, Mars has a nighttime. We can go back to Mars, discussion of Mars from my other book. Thank you for 10 likes. Can we get 20 likes? But Mars definitely has seasons. Mars is kind of like Earth in that sense. Okay. So, we can talk about Mars more as well. I see you have interest in Mars. Okay. And so does a lot of people. So we can go back to Mars. The man of honey wine. Ah. Okay, so we will continue. As soon as I finish coughing. Excusez-moi. Let me share the live again. Oh, good, Stephen. Okay, we will keep going. Further encouragement for the existence of black holes, because remember, so when we observed the supermassive black hole at the center of our own galaxy, that was a big deal too. but it was sort of a roundabout way of finding that we have a supermassive black hole at the center of our own galaxy. So it was not trivial back in the day to first of all accept that black holes are real. They're not just mathematical objects, mathematical models, but actually real, actually a part of nature. Yeah. Anyway, so further encouragement for the existence of black holes came in 1967 with the discovery by a research student at Cambridge, Jocelyn Bell Burnell, of objects in the sky that were emitting regular pulses of radio waves. At first, Bell and her supervisor, Anthony Hewish, thought they might have made contact with an alien civilization in the galaxy. Indeed, at the seminar at which they announced their discovery, I remember that they called the first 4 sources to be found LGM 1 through 4, where LGM stood for Little Green Men. In the end, however, they and everyone else came to the less romantic conclusion that these objects, which were given the name pulsars, were in fact rotating neutron stars that were emitting pulses of radio waves because of a complicated interaction between their magnetic fields and surrounding matter. So, Stephen, I think you're the one who asked about pulsars. Here it is. Here you go. So they had accidentally chanced upon pulsars, which are of course the neutron stars. So, and we talked about how they're pulsars and things like that too when we talked about neutron stars earlier. But anyways, they thought it was aliens, but actually it was pulsars or neutron stars. So this was bad news for writers of space westerns, but very hopeful for the small number of us who believed in black holes at that time. It was the first positive evidence that neutron stars existed. So when a star died, it didn't just become a white dwarf, because that was basically true for the lower mass stars, but we had predicted that the higher mass stars should collapse into neutron stars, and even more higher mass stars should collapse into black holes. So finding the neutron stars is a pretty big deal, because it might give a ray of hope that even black holes are actually real. If a star could collapse to such a small size, because remember, once we started to figure out that we had seen these pulsars or these neutron stars, we also figured out their size, and it's the size of a neutron star is like a 10-mile radius. So that is a very, 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 very small, which means that now we have observed a very compact object indeed in the form of a neutron star with only a 10-mile radius, which means that if you had predicted stars dying and collapsing into even more compact objects, which would be black holes, basically achieving that Schwarzschild radius, achieving the black hole radius, basically achieving a certain radius status, which would make you a black hole. Anyone could be a black hole. Then once you actually find a neutron star out in the wild, in the nature, it gives you hope that maybe black holes are real too, and not just a theoretical concept. Hopefully that makes sense. A neutron star has a radius of about 10 miles. Very small, right? Manhattan is around 10 miles, if I'm not mistaken. Only a few times the critical radius at which a star becomes a black hole. So depending on the star, depending on the mass, etc., if you can become a neutron star, it gives hope that maybe you could get compressed even more for an even more massive star and become a proper black hole, because that's a thing that math supports. That's a thing that was already predicted in theory, but they hadn't found one in nature yet. Nathan, it's all good. I love the chats. Thank you so much. Thank you so much for being here, and thank you for liking the live. We're more advanced now. Why not go back to the moon? We can go back to the moon. It does cost money, though. I think it's for budgetary reasons that we cannot go to the moon constantly. Should apologize to her neighbor. What is this live about other than black holes? Well, today it's mainly about black holes. It can be about anything you want, really, based on your question, hopefully an intelligent one. And it's generally about hanging out, kitty cats, physics, astronomy, cosmology, and astrophysics. And go ahead and ask any question now. Never apologize to your neighbor. And welcome to the live, IU. Thank you for being here. Please do like the live. Can we get 20 likes? So we did go to the moon, but we can't return constantly like a vacation because it's kind of expensive. But maybe it will become less expensive and maybe we can all go because maybe it will become sort of like a vacation at one point. It doesn't have an atmosphere though, so there is that. But the surface is sort of sandy-y and kind of like a beach, as far as I understand. Never been yet. So, not me, but we have as humanity. Have you heard that we are made of stardust? Indeed, I have heard that. Indeed. And we have talked about that on the channel. Thank you for being here. Have I heard? So, a neutron star has a radius of about 10 miles, only a few times the critical radius at which a star becomes a black hole. If a star could collapse to such a small size, it is not unreasonable to expect that other stars could collapse to even smaller size and become black holes. The thing I was saying, which is that if a star can be massive, a massive enough star can be collapsed to the size of a neutron star as at its death, then why not even more massive stars? Because there's such a variety of stars out there. Why not black holes as well? They could collapse down to a black hole. That's a great question. What's a nova? We actually spoke about that in one of the lives, and we can definitely talk about it again. How could we hope to detect a black hole as by its very definition, it does not emit any light? So this is a good question because by definition, a black hole is something that even light cannot escape. The escape velocity from a black hole would be the speed of light in vacuum. So how would you sort of hope to see one if even light cannot escape it? It would be very black. It would be very dark, one would think. It might seem a bit like looking for a black cat in a coal cellar. So it's like looking for a black cat. Fortunately, there is a way. As John Mitchell pointed out in his pioneering paper in 1783, a black hole still exerts a gravitational force on nearby objects. Astronomers have observed many systems in which two stars orbit around each other, attracted toward each other by gravity. So actually, a lot of the stars we see in the sky, like we can't really resolve it, but a lot of them are actually binaries. They're not by themselves. They're not solo. They have a partner, they have a companion, a binary. So lots of objects are sort of these two things that are revolving around each other. They're part of a binary system. So they're basically held together by gravity. They also observe systems in which there is only one visible star that is orbiting around some unseen companion. So there's clues to finding this black cat, if you will, because of its effect with gravitation, because of its effect on other things, and overall because of its gravitation. So one cannot, of course, immediately conclude that the companion is a black hole just because you cannot see, say you see a star and you see that it's probably orbiting around something. You don't have to conclude that it's a black hole. immediately, it might merely be a star that is too faint to be seen. However, some of these systems, like the one called Cygnus X1, are also strong sources of X-rays. So the nice thing is that sometimes you can see other types of radiation from the source, and that has other meaning. So let's see. The best explanation for this phenomenon is that matter has been blown off the surface of the visible star. As it falls toward the unseen companion, it develops a spiral motion, rather like water running out of a bath, and it gets very hot, emitting X-rays. So something that we have seen even with our own galactic center is that the stuff around a black hole can sometimes emit radiation in all kinds of wavelengths, in this case X-rays, because the act of falling towards a black hole causes this acceleration, which causes things to have a radiation. So then, for this mechanism to work, the unseen object has to be very small, like a white dwarf, neutron star, or black hole. And by the way, somebody asked about a nova. A nova is sort of in this category of events that we're describing, but we will get to the specific definition of nova as well. So don't worry and keep watching. And keep coming back to all the lives, because some of the questions are answered across multiple lives. They might not be addressed all at once here today. So for this mechanism to work, the unseen object has to be very small, like a white dwarf, neutron star, or black hole. From the observed orbit of the visible star, one can determine the lowest possible mass of the unseen object. In the case of Cygnus X1, this is about 6 times the mass of the Sun, which, according to Chandrasekhar's result, is too great for the unseen object to be a white dwarf. It is also too large a mass to be a neutron star. It seems, therefore, that it must be a black hole. So if it's too big to be a white dwarf, which has a Chandrasekhar limit of around 1.4 solar masses, if it's too large of a mass to be a neutron star, then the other conclusion is that it's a black hole, especially if you can't see it and you can see other things doing things around it, then those are the clues. Hello, El Challen. I see one question here. Do stars get their light from the sun? No. I think this is the best question so far from you, Faze. Stars, in fact, do not get their light from the sun. They have their own light. To be a star, you have to have a nuclear reactor in your belly, and you have to emit your own radiation, light, energy, heat, neutrinos, all kinds of things, in fact. And generally, you have quite a bit of mass. And that gravitation, instead of collapsing on itself, a star continues to be a star as long as it continues to burn its fuel and makes nuclear reactions happen within it. And all of the light from stars are their own. The luminosities of various stars are because of their own nuclear power. So the light of stars is indeed not from the sun. The light from Venus is reflected light off of the sun. Venus is the third brightest object in the sky, I believe, after the sun and the moon for us on Earth. And that light is because of sunlight. Sunlight reflected off of Venus and its atmosphere gives it that bright look that we can see. But indeed, a star has its own source. And the sun is an example of a star. Okay, so Cygnus X1, because it has a mass of 6 times the mass of the sun, that's too big to be a white dwarf because of the Chandrasekhar limit that we talked about. You can't be a white dwarf if you're that massive. And it's also too large a mass to be a neutron star. It seems, therefore, it must be a black hole. There are other models to explain Cygnus X1 that do not include a black hole, but they're all rather far-fetched. A black hole seems to be the only real natural explanation of the observations. Despite this, I had a bet with Kip Thorne. So Stephen Hawking is saying that he had a bet with Kip Thorne of the California Institute of Technology that in fact, Cygnus X1 does not contain a black hole. This was a form of insurance policy for me. I have done a lot of work on black holes and it would all be wasted if it turned out that black holes do not exist. But in that case, I would have the consolation of winning my bet, which would bring me 4 years of the magazine Private Eye. In fact, although the situation with Cygnus X1 has not changed much since we made the bet in 1975, this book was written first in 1988, and then we're looking at we're reading the 10-year edition here, 10-year anniversary edition here. So he had a bet with Kip Thorne of Caltech that this might not be a black hole. In fact, although the situation with Cygnus X1 has not changed much since we made the bet in 1975 at the time of writing this book, there is now so much other observational evidence in favor of black holes that I have conceded the bet. I paid the specified penalty, which was a 1-year subscription to Penthouse, to the outrage of Kip's liberated wife. I'm not sure what this means, but that's what he is saying. We also now have evidence for several other black holes in systems like Cygnus X1 in our galaxy and in 2 neighboring galaxies called the Magellanic Clouds. So we talked about the large Magellanic Cloud and the small Magellanic Cloud galaxies, irregular galaxies, remember, and that's what he's mentioning now. The number of black holes, however, is almost certainly very much higher. In the long history of the universe, many stars must have burned all their nuclear fuel and have had to collapse. The number of black holes may well be greater even than the number of visible stars, which totals about 100,000 million in our galaxy alone. The extra gravitational attraction of such a large number of black holes could explain why our galaxy rotates at the rate it does. The mass of the visible stars is insufficient to account for this. We also have some evidence that there is a much larger black hole with a mass of about 100,000 times that of the Sun at the center of our galaxy. So he did know about the supermassive black hole at the center of our own galaxy, which is good. Indeed, Sagittarius A star. Stars in the galaxy that come too near this black hole will be torn apart. So Sagittarius A star is a supermassive black hole, which of course makes a lot of matter accrete into it, making it kind of bright around this black hole, and things, objects, stars, even around the black hole is torn apart because of it. So torn apart by the difference in the gravitational forces on their near and far sides. So that is tidal forces on those stars. So think about the moon and its tides on us and our oceans on the earth. Now think about a black hole's tidal forces on stars that are nearby. It causes tidal forces on those stars, tears them apart, and does a lot of things, which makes actually Sagittarius A star kind of give itself away at the center of our own galaxy here on the Milky Way, in the Milky Way. There remains and gas that is thrown off other stars. 1 second. There remains, actually give me 1 second. There remains, as in the stars remains, and gas that is thrown off other stars will fall toward the black hole. As in the case of Cygnus X1, the gas will spiral inward and will heat up, though not as much as in that case. So in Cygnus As in the case of Cygnus X1, the gas will spiral inward and will heat up, though not as much as in that case, in the case of Cygnus. It will not get hot enough to emit X-rays, but it could account for the very compact source of radio waves and infrared rays that is observed at the galactic center. I believe that we have seen X-rays as well, though, at this point from our galactic center, but some of these results may have continued to come after the book was written. It is thought that similar but even larger black holes with masses of about 100 million times the mass of the sun occur at the centers of quasars. So, you know, even more extreme situations in quasars. For example, observations with the Hubble telescope of the galaxy known as M87 reveal that it contains a disk of gas 130 light years across, rotating about a central object 2,000 million times the mass of the sun. This can only be a black hole. 2,000 million times the mass of the sun. 2,000 million times. And by the way, another thing I wanted to mention quickly that I mentioned last night as well is that a black hole is a stellar remnant. It's very massive. The most massive stars will die as a black hole. But after that, a black hole can continue to grow in mass by eating more material after it has turned into a black hole already. And that is really how supermassive black holes become supermassive. It is not the case that you have to start as that supermassive state. You know what I mean? Like our supermassive black hole at the center of our own galaxy and other galaxies too, those supermassive black holes really ate more material accreted into that supermassive black hole to make it more and more massive over time. This 2,000 million solar mass black hole did not start as that, okay? So if you're small now, don't worry, you can be big over time. Yes, it's because of eating more material over time. Surrounding material can accrete into the black hole, can slowly lose gravitational energy and go into the black hole. And that's how it continues to get bigger and bigger. So this can only be a black hole, the 2,000 million times the mass of the sun one. Matter falling into such a supermassive black hole would provide the only source of power great enough to explain the enormous amounts of energy that these objects are emitting. I'm about to finish the chapter, so hang on. As the matter spirals into the black hole, it would make the black hole rotate in the same direction, causing it to develop a magnetic field rather like that of the Earth. Very high energy particles would be generated near the black hole by the infalling matter. So these high energy particles that the black hole makes accelerate towards the black hole, like basically the infalling matter is not just infalling at some constant velocity. Most of the time it would be accelerating towards the black hole, right? And this type of infalling matter actually create a lot of radiation, which makes certain black holes kind of bright around it because of the infalling matter. Okay, sometimes we call it accreting matter. The magnetic field would be so strong that it could focus these particles into jets ejected outward along the axis of rotation of the black hole, that is in the directions of its north and south poles. Just like we have north and south poles, the Earth, and we have a magnetic field, so could a black hole, and it could, oh my gosh, it could make the very high energy particles focused around these north and south poles. Such jets are indeed observed in a number of galaxies and quasars. One can also consider the possibility that there might be black holes with masses much less than that of the sun. Such black holes could not be formed by gravitational collapse because their masses are below the Chandrasekhar mass limit. Stars of this low mass can support themselves against the force of gravity even when they have exhausted their nuclear fuel. So we would call it sort of a cold star. Once a star has kind of exhausted its nuclear power and it doesn't collapse, then it's a very cold star. So stars of this low mass can support themselves against the force of gravity even when they have exhausted their nuclear fuel. Low mass black holes could form only if matter was compressed to enormous densities by very large external pressures. Such conditions could occur in a very big hydrogen bomb. The physicist John Wheeler once calculated that if one took all the heavy water in all the oceans of the world, one could build a hydrogen bomb that would compress matter at the center so much that a black hole would be created. Of course, there would be no one left to observe it. A more practical possibility is that low mass black holes might have been formed in the high temperatures and pressures of the very early universe. So low mass black holes are not completely out of the question. I think I saw a sort of a interesting question here. Why don't we send a telescope down a black hole? We could, but it would not come back. And information cannot come back from inside of a black hole because even light cannot escape a black hole. So even if you sent a telescope and could communicate with it, that communication would not come out of the black hole anymore. So it's kind of like a waste of efforts to send anything down a black hole. You would not expect to get the information out. Since you asked about novas, we will absolutely cover them specifically. But the short answer is no, not quite. But we will talk about novas. Thank you so much for the questions. Thank you so much for being here. Welcome to the live, and please do like the live. Can we get 20 likes? So, we talked about the low mass black holes that could have been, in the early universe. Black holes would have been formed only if the early universe had not been perfectly smooth and uniform, because only a small region that was denser than average could be compressed in this way to form a black hole. But we know that there must have been some irregularities, because otherwise the matter in the universe would still be perfectly uniformly distributed at the present epoch. Who is fighting? So the irregularity that we just now mentioned is going to be extremely important. Hello, Rose. We know that there must have been some irregularities in this smooth universe, because otherwise matter would still be perfectly uniformly distributed at the present epoch instead of being clumped together in stars and galaxies. Whether the irregularities required to account for stars and galaxies would have led to the formation of a significant number of primordial black holes. So primordial black holes is a question that we must try to answer, that does come up. We haven't heard about them too much yet in the book, and we haven't discussed them too much on this channel yet. But primordial black holes is also something to consider. But whether these irregularities required to account for stars and galaxies would have led to the formation of a significant number of primordial black holes clearly depends on the details of the conditions in the early universe. So if we could determine how many primordial black holes there are now, we would learn a lot about the very early stages of the universe. Primordial black holes with masses more than 1,000 million tons, the mass of a large mountain, could be detected only by their gravitational influence on other visible matter or on the expansion of the universe. However, as we shall learn in the next chapter, black holes are not really black after all. They glow like a hot body. And this is what Stephen Hawking worked on. So this is where we're getting very close to... Thank you, Kimmy. Thank you for being here. Hello, El Challen. Hello, Kimmy. Thank you so much. You know what? I should post, I should get a mailbox and put that on the channel so that you can send your gifts, such as a projector, if you'd like. So, primordial black holes with masses more than 1,000 million tons could be detected only by their gravitational influence on other visible matter. But getting hot, close to the topic that Stephen Hawking worked on, which is black hole radiation, Hawking radiation, is this sentence right here. We shall learn in the next chapter that black holes are not really black after all. They glow like a hot body. And the smaller they are, the more they glow. So paradoxically, smaller black holes might actually turn out to be easier to detect than large ones. And the next chapter is called Black Holes Ain't So Black. So we will do chapter 7 next. Let me see everybody's questions and whatnot. Do you have any questions on the matters so far, on the topic so far? I see lots happening in the chat. Thank you so much. Thank you, Kimmy. Did you like the live? Could you please like the live? Thank you so much. Please do like, please do subscribe, please do share. Much appreciate. Thank you for being here. Thank you for liking the live. Oh, thank you. I love the hearts from you. Thank you so much. Dang, haven't been in a while. What's up? Hello, Marky Mark. Hello, FaZe. Hello, Wonder Boy. Hello, Doro. Black holes are stellar remnants. So they do, when stars die, the most massive ones do make black holes. So black holes were once stars. But then we just mentioned primordial black holes, and we were talking about how those could have come to be, maybe, and how black holes ain't so black. They do emit some sort of radiation, Hawking radiation in this case, which Stephen Hawking, the guy who wrote this book, worked on. So next topic, or the next segment, is going to be on black holes ain't so black. And it's going to be on Hawking radiation. Yes, so a star can die with an explosion, generally, called a supernova. And depending on the initial mass of the star, it becomes either a white dwarf or a neutron star or a black hole. Those are the, in fact, FaZe, you should go to my live, which is called Stellar Remnants. It was from a while ago. Under my live tab, on the channel, under my live tab, if you see a live called, I believe it's called, probably named it Stellar Remnants, then you will hear all about the things you're asking about, nova, supernova, although I will cover nova again because you asked. So I will, of course, cover it again. But stellar remnants might be a live that you're interested in because we talked about white dwarfs, neutron stars, and black holes in that live. And the stars, when they die, become either a white dwarf or a neutron star or a black hole. I'm going to take a quick break and then come back to talk about black holes ain't so black. It won't be a 4-hour water break. So give me a second. I do actually have to use the bathroom. It's Monday. I go late on Mondays. So I'll be back. Don't you worry. And can you please like the live? Doro, can you have people please like the live? And can we get 20 likes? I'm going to start the next topic. Black holes ain't so black. So definitely I will be back. But I have to pee. Thank you so much, everybody. She will be on the iPad laughing for hours. Aw. Baji is here, you guys. Okay. Sorry about that. I see some of you have gone to sleep, which is a good thing. It is Monday night after all. Reset, off to sleep. Good night, chat. If anyone's there, much love. Good night to the people who are good nighting. Aww. It was Harper. That's true, Harper. Harper banned everybody and left. El Challen. I too gotta call it. You probably have 15 men waiting on you. More hurry the frick uppies. Okay, I see the comments. Somebody asked about Antarctica. We can talk about the treaty. Oh. Too bad everybody's gone. Steven, are you still here? What time is it? It's 1 in the morning. Okay. You have to detest. You have to detest Rose. See, sorry about the laughing, Doro. You might be trying to sleep. Whoops. Combat sports. Okay, so combat sports. Any other questions from you? El Challen, combat sports, still here. Lovely. You sleep 5 hours per night. Kind of. Actually, I'm kind of hungry right now. Kind of hungry. Let's see. Let's start this chapter at least a little bit, and then we will continue tomorrow. So, Chapter 7, Brief History of Time by Stephen Hawking. Black holes ain't so black, after all. Because as we know, Hawking worked on black hole radiation, Hawking radiation, named after him. And what that means is, just like other objects, black holes can still be emitting some form of black body radiation. Ooh, Phase is still here. Are we in danger of black holes? I mean, maybe not. I don't think anything imminent is happening. Okay, before 1970, my research on general relativity had concentrated mainly on the question of whether or not there had been a Big Bang singularity. So the other type of singularity in nature that we know of is the Big Bang, along with black holes being a singularity. kicking you out, El Chalin? Did you ask to be mod and were people mean to you? I'm so sorry. You can be here. Nobody's kicking you out. I'll make sure of it. A lot was happening in the chat, so I didn't really see. Were people mean to you for asking to be mod? Oh no. You are most welcome. Stay. Stay, El Chalin. Stay. Thank you for being here. Can you please like the live? Can we get 20 likes? Can we? Indeed, combat sports. Indeed. Okay. Indeed, they don't merge very easily, do they? Do they? Indeed, they don't. Combat sports, are you going to come up with a bigger theory that subsumes both? Because that would be most excellent. Most excellent. Okay. Before 1970, my research on general relativity had concentrated mainly on the question of whether or not there had been a Big Bang singularity, says Stephen Hawking in his book Brief History of Time. When is recess? We just had it. There was a big break. What were you doing then, Faze? Now it's time to concentrate again on the lesson, which is black holes. Ain't so black. Break is done, and we're reading again. If I could merge them, you can then call me Kombenstein Sports. Very nice. However, one evening in November that year, shortly after the birth of my daughter Lucy, I started to think about black holes as I was getting into bed, says Stephen Hawking. My disability makes this rather a slow process, so I had plenty of time. At that date, there was no precise definition of which points in space-time lay inside a black hole and which lay outside. I had already discussed with Roger Penrose the idea of defining a black hole as a set of events from which it was not possible to escape to a large distance, which is now the generally accepted definition. It means that the boundary of the black hole, the event horizon, is formed by the light rays that just fail to escape from the black hole, hovering forever just on the edge. It is a bit like running away from the police and just managing to keep one step ahead, but not being able to get clear away. Light rays that just fail to escape from the black hole, hovering forever just on the edge. Isn't that cool? Suddenly, I realized that the paths of these light rays could never approach one another. If they did, they must eventually run into one another. It would be like meeting someone else running away from the police in the opposite direction. You would both be caught. Or, in this case, fall into a black hole. But if these light rays were swallowed up by the black hole, then they could not have been on the boundary of the black hole. So the paths of light rays in the event horizon had always to be moving parallel to or away from each other. Another way of seeing this is that the event horizon, the boundary of the black hole, is like the edge of a shadow, the shadow of impending doom. If you look at the shadow cast by a source at a great distance, such as the sun, you will see that the rays of light in the edge are not approaching each other. If the rays of light that form the event horizon, the boundary of the black hole, can never approach each other, the area of the event horizon might stay the same or increase with time, But it could never decrease because that would mean that at least some of the rays of light in the boundary would have to be approaching each other. In fact, the area would increase whenever matter or radiation fell into the black hole. Or if two black holes collided and merged together to form a single black hole, the area of the event horizon of the final black hole would be greater than or equal to the sum of the areas of the event horizons of the original black holes. This non-decreasing property of the event horizon's area placed an important restriction on the possible behavior of black holes. I was so excited with my discovery that I did not get much sleep that night. The next day I rang up Roger Penrose. He agreed with me. I think, in fact, that he had been aware of this property of the area. However, he had been using a slightly different definition of a black hole. He had not realized that the boundaries of the black hole, according to the two definitions, would be the same, and hence so would their areas, provided the black hole had settled down to a state in which it was not changing with time. The non-decreasing behavior of a black hole's area was very reminiscent of the behavior of a physical quantity called entropy, which measures the degree of disorder of a system. It is a matter of common experience that disorder will tend to increase if things are left to themselves. One has only to stop making repairs around the house to see that. One can create order out of disorder. For example, one can paint the house, but that requires expenditure of effort or energy and so decreases the amount of ordered energy available. A precise statement of this idea is known as the second law of thermodynamics. Entropy is always increasing. It states that the entropy of an isolated system always increases and that when two systems are joined together, the entropy of the combined system is greater than the sum of the entropies of the individual systems. For example, consider a system of gas molecules in a box. The molecules can be thought of as little billiard balls continually colliding with each other and bouncing off the walls of the box. The higher the temperature of the gas, the faster the molecules move, and so the more frequently and harder they collide with the walls of the box, and the greater the outward pressure they exert on the walls. Suppose that initially the molecules are all confined to the left-hand side of the box by a partition. If the partition is then removed, the molecules will tend to spread out and occupy both halves of the box. At some later time, they could, by chance, all be in the right half or back in the left half, but it is overwhelmingly more probable that there will be roughly equal numbers in the two halves. Such a state is less ordered or more disordered than the original state in which all the molecules were in one half. One therefore says that the entropy of the gas has gone up. Similarly, suppose one starts with two boxes, one containing oxygen molecules and the other containing nitrogen molecules. If one joins the boxes together and removes the intervening wall, the oxygen and the nitrogen molecules will start to mix. At a later time, the most probable state would be a fairly uniform mixture of oxygen and nitrogen molecules throughout the two boxes. This state would be less ordered and hence have more entropy than the initial state of two separate boxes. The second law of thermodynamics has a rather different status than that of the other laws of science, such as Newton's law of gravity, for example, because it does not hold always, just in the vast majority of cases. Entropy increases while we observe locally, universes get organized. The probability of all the gas molecules in our first box being found in one half of the box at a later time is many millions of millions to one, but it can happen. However, if one has a black hole around, there seems to be a rather easier way of violating the second law. Just throw some matter with a lot of entropy, such as a box of gas, down the black hole. The total entropy of matter outside the black hole would go down, one could, of course, still say that the total entropy, including the entropy inside the black hole, has not gone down. But since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. It would be nice then if there was some feature of the black hole by which observers outside the black hole could tell its entropy, and which would increase whenever matter carrying entropy fell into the black hole. Isn't that curious? Following the discovery described above that the area of the event horizon increased whenever matter fell into a black hole, the area of the event horizon increased whenever matter fell into a black hole, a research student at Princeton named Jacob Bekenstein suggested that, so not Einstein, but Bekenstein, suggested that the area of the event horizon was a measure of the entropy of the black hole as matter carrying entropy fell into a black hole, the area of its event horizon would go up, so that the sum of the entropy of matter outside black holes and the area of the horizons would never go down. Wow. So this leads to something very interesting, because now we've got thermodynamics involved with black holes, and if a black hole has entropy, then it ought to also have a temperature. And this temperature will lead to the next discussion, which we will continue next time. I got a few things to do, so if you have any questions, let me know in the chat. I'm still around. Is there a north, south, east, or west of a black hole? Yes. Indeed there is. In space. I guess north of what, south of what? You need to give us an object. And then the object may have a north, south, west, or east. Are you leaving? No, I'm still around. I'm still around. I think I want to pick up entropy and temperature of black hole next time, but I'm still going to be around. I have a couple of things to do in the kitchen that you can hear me doing. Okay. So the next part is going to be very exciting. Entropy, temperature, black hole, that's going to be giving us the next part, and the famous Hawking radiation, I believe. So we will pick up from this. This is page 107 of this book, Black Holes Ain't So Black, Stephen Hawking, Brief History of Time. I have a few things I got to do in the kitchen that I will start doing right now with you on the live. Thank you everybody so much for being here. El Challen, Phase, Combat Sports, thank you. And if you're coming into the live right now, then you feel free to rewind and go and watch the whole thing. Okay? In fact, let me leave you with a few pictures. I know Faze was asking about certain pictures. Let me give you some pictures to look at. Let me give you some pictures to look at. That would be good. And let me know if you have any questions about them, because I'm still around. I'll still see the chat. How old are you? Good question, El Challen. How old are you? show you the book here. Put that there. Show you this picture that I couldn't show you earlier. Because you stuck to the end of the live, we will be able to show you right here, right now. Let me get out of this chair. Oh, hi, Suji. Here's Sachi Mama. And there you go. You can look at this picture as I do some things in the kitchen. Look at this picture. Putting you on this paper towel right here. Wait. It's not quite working yet. Here. Maybe like that. There. You can see that, like that. Thank you for being here. Welcome to the live. Please rewind if you want to see the whole thing. And I will show you this diagram while I do a few things in the kitchen. And you can ask me any questions in the chat while you look at this. I'm holding this open. This is a diagram from the chapter that we were just discussing called Black Holes from the book Brief History of Time by Stephen Hawking. This is distance from center of a star. On the x-axis here, time is on the y-axis, and you can try to read the rest as I do this other thing here. Give me a second. And let me see. So this is so remember the part we were talking about with stars and black holes and things like that. So the page on this side kind of explains this figure right here. So let me read that real quick. So the picture that we now have from Oppenheimer's work is as follows. The gravitational field of the star changes the paths of light rays in space-time from what they would have been had the star not been present. The light cones, so this is light ray emitted after event horizon forms. This is the singularity. This is the interior of the star, light ray emitted before event horizon forms. Light cones, light ray emitted at the time of the event horizon, at the time that the event horizon forms. So this is sort of where the star is going from being a star to maybe a black hole. The light cones, which indicate the paths followed in space and time by flashes of light emitted from their tips, are bent slightly inward near the surface of the star. This can be seen in the bending of light from distant stars observed during an eclipse of the sun. As the star contracts, the gravitational field at its surface gets stronger and the light cones get bent inward more. This makes it more difficult for light from the star to escape, and the light appears dimmer and redder to an observer at a distance. Eventually, when the star has shrunk to a certain critical radius, so it's become very compressed, in other words, very compact. Eventually, when the star has shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light cones are bent inward so much that light can no longer escape. So this is showing that, where light can no longer escape. Okay, so this is the interior of the star. Light ray emitted at the time the event horizon forms is right there. So see how it gets, or this way, This way is the distance from the center of the star, with 0 being right here, and this is time on the y-axis. Okay, so eventually when the star has shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light cones are bent inward so much that the light can no longer escape. According to the theory of relativity, nothing can travel faster than light. Thus, if light cannot escape, neither can anything else. Everything is dragged back by the gravitational field. So one has a set of events, a region of space-time, from which it is not possible to escape to reach a distant observer. So you would not basically be able to get the information out from the black hole. This region is what we call the black hole. Its boundary is called the event horizon, and it coincides with the paths of light rays that just fail to escape from the black hole. So the paths where it just fails is the event horizon, okay? And after that, it's all black hole. See how it gets from lighter to more and more dark and black? That's because after the event horizon, nothing's coming out of there. It's all black hole, okay? No more information can be obtained or gotten out because even light can't escape. So there's nothing coming out again. And the surface, sort of just where light cannot escape anymore, that surface is called the event horizon. Light ray emitted at the time the event horizon forms. See? After that, it's done. Light ray emitted after event horizon forms. So everything, all the light kind of just stays in after that. And that's why right here we call that a singularity. It's a singularity because it's sort of this infinite density thing that's happening in space-time. Light cannot even escape that, and gravitation is very high right there, and it just goes from lighter to darker to darker to totally dark. That's what you see here, okay? Okay. I have to do a couple things here. I will stay online and see your comments and messages as I do this. Is black holes dark matter? So dark matter, the nature of dark matter is yet unknown and a topic of research. It is one of the biggest questions of the universe. The first one being what is dark energy, and the second one being what is dark matter. So whether dark matter is black holes or compact objects that could include black holes, that is a great thought. We talked about dark matter candidates, and indeed compact halo objects in our own galaxy were considered to be a candidate for dark matter, but we sort of disregarded them and did not think that they accounted for most of the dark matter, say, in our own galaxy. So at this time, we don't quite know what dark matter is. Black holes could have a role in dark matter. They could, or they could not. It's really not confirmed. We don't know yet. It's a topic of research. But it's a great question. So thank you. And yeah, you should definitely also check out my live called, I might have called it Dark Matter Candidates. Anyway, there was probably at least a few lives where I discussed dark matter candidates. So definitely go check that out. We actually talked about how dark matter candidates included at one point neutrinos, then they came up with WIMPs, or weakly interacting massive particles. And then we also talked about machos, sort of as an opposite to the WIMPs, which included compact halo objects, which could include things like black holes. But because black holes and other compact objects would still give us a lensing effect, so because of course these things still have an effect on gravitation,
we can actually sort of estimate how much of these things are there in the galaxy and in the halo. And we did not think that there was enough to account for all of the dark matter that we would, for example, need in our own galaxy. Now, dark matter is something that exists just in the universe, in other galaxies, and other places as well. It's not just a question of our own galaxy, it's a cosmological question as well as an astronomical question. But say, for example, if you were interested in only understanding the dark matter in our own galaxy, even there, compact halo objects don't quite explain all of it. So we would have to figure out still basically all of it, if that makes sense. So, but it's a great question. Somebody asked, is a black hole dark matter? And this was my answer to that. Thank you so much for asking. To do a little chore has to do with are living stars the opposite of black holes? I don't know if living stars. Sure, that is one way of putting it. Black holes do start as stellar remnants. So, well, at least there could be. Actually, there could be some other types of black holes as well, like primordial black holes. But the black holes that we discuss in the context of stars are coming from a star's death. So they are an example of a stellar remnant. So indeed, a black hole is an example of a stellar remnant, what is left behind after a star dies. But there are some other types of stellar remnants as well for lower mass stars. So the lowest mass stars will become white dwarfs, more massive stars will become neutron stars, and the most massive stars will become black holes. So in that sense, sure, the opposite of a black hole you may consider to be a living star. But I don't know if I would put it quite like that, but sure. In this context, yeah, I see what you're saying. Basically, a star emits a lot of light. It dies, becomes a black hole. No light can escape. I can kind of see the analogy. So, sort of, yes. And hopefully next time we will get a deeper insight into black holes, though. They're kind of their own type of object. So, you know, once something collapses to the level of a black hole, what I would sort of say about black holes is that they're their own object at that point. So even though they may come from the death of a star, at this point, a black hole is a black hole. It kind of stands on its own. We don't have to think about the star too much. A black hole will do its own things. It may become a supermassive black hole if it continues to eat more material. So I would almost want to sort of separate it from the star at that point. But if it helps you to understand these things, then go for it. Good night, El Challen. Thank you for coming to the live. Appreciate you.
Suji. Taking out all the recycling here.
Black matter. Yeah, indeed. That is one way of putting it, for sure. For sure, that is a way to put it. Indeed. I'm just doing a couple things here in the kitchen. Keep your questions coming. Ask away, and I'll try to address them either tonight or next time, which will be tomorrow. Hi, Suji. are very cold. Had to make them warmer. Perhaps now you can look at a kitty cat. Look, here is Baji, here is Sachi, here is my Fuji bubble. With the thanks to the universe, and there's a lot of recycling that I have to take out. A ton of recycling. Can a star be anything other than a black hole when it dies? Yes, I was just mentioning the three possibilities when a star dies: white dwarf, neutron star, and black holes. Those are the three things, and we talked about it. Go ahead and play my previous lives, and hopefully you will see more information on this phase. Indeed, a star can be other things. A star can be either a white dwarf, a neutron star, or a black hole. And if you keep coming to the lives, I might cover all of that again for your benefit, because we have spent time talking about this, but always happy to again. And here's a kitty cat. While you think about more questions for me, go ahead. Go ahead, and thank you so much indeed for being here. Welcome to the live, and please rewind and watch the whole thing, and please do like the live. Can we get 20 likes? Hi, Sachi Mama. Get the dishwasher started here. We're like stars in a way. We sure are. Indeed, we are like stars. That's correct. That's a good analogy. Yay! এটা কি সাচি মাম্মা নাকি হ্যাঁ? এটা কি সাচি মাম্মা নাকি হ্যাঁ? Oh my god. Oh my god. Oh my goodness. Oh my goodness gracious me. Oh my goodness gracious me. Oh, Sachi Mama. Sachi Mama is a very good mama. Mwah. এটা কি সাচি মাম্মা নাকি হ্যাঁ? সোনা মাম্মা, সোনা মাম্মা তো সোনা, ভীষণ সোনা। এখানে সব সোনারা থাকে, বুঝেছো? সোনা ছাড়া কেউ না, ভীষণ সোনা। এখানে কি সব সোনু মনুরা থাকে? হ্যাঁ, সোনু মনু তো তুমি, সোনু মনু, সহ্য হয় না। তোমার নাম কি সোনু মনু? তোমার নাম কি সোনু মনু? তোমার নাম কি সোনু মনু? হ্যাঁ, সোনু মনু নাকি তুমি? হ্যাঁ। Oh my goodness, এত কিউট না এই মেয়েটা।
guys. এত কিউট না তুমি, ভীষণ কিউট তুমি জানো, ভীষণ কিউট। ও মাই গুডনেস, এই দেখো কত সোনা, এই দেখো কত সোনা তুমি, ওরে বাবলে, এটা একটা সোনা মেয়ে, এটা একটা ভীষণ সোনা, এক্সট্রিম সোনো মনো, ভীষণ সোনা, ভীষণ সোনা, এক্সট্রিম সোনা, এক্সট্রিম সোনো মনো। The comment unnecessarily look nice and blue. I'm seeing comments on my channel. Food is about to fall. I must be ready with the bowls. You can see. Here, Baji. I'm doing a little bit of weight control for Baji here. Because he needs to lose some and Suji needs to gain some. So indeed, I am working on that, and I was washing the dishes, so had to put the new ones down for them here to make sure that they had their snacks in a bowl. Caught it right at the caught it right on time. There you can see Baji. How far did you go in school? What if the earth is glowing because life and not the sun? What if the earth is glowing? look at this. More books coming. Boston Public Library. This book is called The Little Book of Cosmology. We will talk about this as well. And we have this book right here. Very short introduction. Got that as well from the library. Soon on the channel. So, how far did you go? Do you mean the distance to my school, or do you mean higher education? Baji's still looking for tidbits. Well, I have a PhD, so graduate school. There's some. Indeed.
Do you have any questions? Oh, that's a good question.
Do I have a question? Maybe.
Interesting outlook for sure. So I just sometimes get things that have brought it to me themselves. Fuji. No Fuji. Orange, no? Difficult task. Very difficult task indeed. Change the litter robot garbage bag. So we do that. Hello, 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 hello. Maybe let's do some Kit Kats. Baji is in loaf mode. Let me show you. Hello, Baji. Hi, Baji. Hi. Oh my goodness, Baji. Oh my goodness. Look at that. Look at that. What do you think of this question, Baji? What do you think? Baji's in a love mood. তুমি কি লোভী? তুমি বাজি, তুমি ছেলে তো, তুমি তো ভালো ছেলে, তুমি তো একটা ভালো ছেলে, তুমি তো বিরাট ভালো ছেলে, ভীষণ ভালো ছেলে তো তুমি। একটা তো ভালো ছেলের মতো আছে এখানে বাজি, কত সুন্দর, একটা তো ভীষণই ভালো ছেলে তুমি। ভালো ছেলে কাকে বলে দেখেছো? কত ভালো ছেলে, কত ভালো ছেলে তুমি। Bumped my coffee table by mistake. Baji. Baji's reaching for the live stream. He is. Alright guys, I think we're gonna say goodnight. We're gonna say goodnight. Good night, sleep tight. Good night and sleep tight. That's what we have to say. Hi, Baji wants to hold my hand. He does. He loves this phone case. And he wants to hold my hand. Hi. Oh. Oh. Good night. Good night, everybody. Baji says good night. Good night. Hee hee hee, Baji. We're gonna go upstairs and we're gonna have lots of cuddle time. Baji and his siblings. Lots of snuggles. We've done all the chores that we wanted to. Now it's cuddle time. Snuggle time. Cuddle and snuggles. Cuddles and snuggles. That's what we're gonna do now. Cuddles and snuggles. With a very long-armed kitty cat indeed. Extremely long arms. Has anyone seen such long arms? Elongated. Indeed, quite elongated. Ho ho ho.